Hi, I'm Mark Barsamian. In this video, I'll be continuing a discussion of functions. I'll be discussing inverse functions and compositions of functions. So our topics will be inverse functions, the definitions and the graphs, and the injective and surjective properties of those, and function composition, the definition, injective and surjective properties of compositions of functions, and the relationship between function composition and inverse functions. The reading is section 1.3, just a couple of pages, and the corresponding homework is this collection of 7 exercises. Now recall from the previous video that we talked about relations from one set to another set. To say that a relation R is a relation from S to T means just simply that R is a subset of the Cartesian product, S cross T. In other words, R is a set that contains ordered pairs of the form little s, little t, where little s is in capital S and little t is in capital T. And remember that the set on the left, the set S, is called the domain of the relation, and the set T is called the range of that relation. And remember that every relation has an inverse relation, denoted this way. That's the relation obtained by just reversing the order of the elements in the ordered pairs for R. So every relation has an inverse relation, and it's denoted that way. And the inverse relation is a relation that goes from set T back to set S. And recall the definitions of function. A function is a relation from x to y. So a function from x to y is a relation from x to y that has an extra property. For each x in the domain set, there is exactly one y in the range set, such that that ordered pair is in the relation. And we denote that special y value as using this symbol, y equals f parentheses x. So the formal expression that expresses that a relation is a function is this. For every x in the domain, there exists exactly one y in the range such that that y equals f of x. And remember the definition of a bijective function. That's a function that is both injective and surjective. And remember that written formally, it looks like this. For every y in the range, there exists exactly one x in the domain such that f of x equals y. So these two expressions, these two formal expressions, look very similar, but they are subtly different. The orders of the quantifiers are different. In the expression up here, the x is in front, and the expression down here, the x is the second quantifier. And the expression up here, the y is in the second quantifier, and the expression down here, the y is in the first quantifier. Now I want to talk about inverse functions. We saw in the previous video that when R is a relation from capital S to capital T, there's an associated inverse relation. And we also saw that the inverse relation might not be qualified to be called a function. Now consider the special case where the relation is actually a bijective function from x to y. In this special case, for each y in the range, there is exactly one x in the domain such that this equation is true. In this special case, the inverse relation, denoted with this symbol, is actually qualified to be called a function, and we call it the inverse function. So we use the same symbol that we used earlier for inverse relation, but if we use it in the situation where f is a bijective function, then this thing, instead of being called the inverse relation, is called the inverse function. But it's the same thing. It's the inverse relation for f. It's just qualified to be called a function. And here's how it works. Now this inverse function is a function whose domain is y and whose range is x. So I have to describe how it works. I have to describe what happens when you put in a y value. The result is that symbol stands for the unique x value such that f of x equals y. So we could also do this in the following way. We can just say that this symbol, the f superscript -1 parentheses y equals x means the same as this symbol, y equals f of x. So let's do an example. At the end of the previous video, we found that this function is bijective. The function with domain, the set of all real numbers except 3, and range, the set of all real numbers except 1, given by this formula. Question is, how do we find the inverse function? Well, the formula for f of x could be thought of as an equation solved for y in terms of x. So that equation illustrates what happens when you feed an x value into the function f. The function f does all this stuff to it and spits out that value of y. Well, if we solve that equation for x in terms of y, we get this equation. Now, what's that equation express? That equation expresses that if you do this stuff to y, the result will be the x. Well, that's what the inverse function does. It takes the value of y and produces the corresponding value of x. So in other words, this equation corresponds to the formula for the inverse function. So the inverse function can be written this way. So you take the original equation, you solve for x in terms of y, and you get an equation that can be used to write the expression for the inverse function. The example above illustrates this general procedure to find the inverse function for a function given by a formula. If you're given a bijective function described by a formula, then starting with that associated equation, that is y equals some expression involving x, solve that equation for x in terms of y to get a new equation of this form. X equals some expression involving y. That new equation describes the operation of the inverse function. That is, the inverse function is the function with domain, capital Y, and range, capital X, that's described by this formula. Whatever that new expression involving y was, that's the right-hand side of the function form for the inverse function. F inverse y equals that new expression involving y. So you get x by computing f inverse of y using that new expression involving y. Now keep in mind, once you have the formula for the inverse function obtained in this form, you can change the variables. So you could replace the y with t, and you could replace the x with s. So then you'd have s equals some expression involving t. And then you could replace the s with y, and you could replace the t with x, and we could get y equals some new expression involving x. So if you prefer to have functions with x as the variable, you can always get them later. Now what about the graphs of inverse functions and inverse relations? Recall from the definition of the inverse relation that the ordered pairs for the inverse relation are obtained by reversing the order of the elements in the ordered pairs for the original relation. So that's, of course, also true for the special case where the relation R is actually a bijective function, and the inverse relation, denoted f superscript -1, is actually qualified to be called a function then, and that's called the inverse function. So the graph of the inverse function is also obtained by reversing the order of the elements in the ordered pairs. So for instance, let's consider this function with domain, the set of all real numbers, and range, the set of all real numbers, defined by f of x equals x cubed. This function is bijective, so the inverse relation is qualified to be called the inverse function. Its formula is this. Let's look at the graphs. The graph of f of x equals x cubed has some famous points. The graph of the inverse function has the corresponding points with the coordinates reversed. Go on. Consider this function, f of x equals x squared. Notice that the graph of f fails the horizontal line test. That horizontal line crosses the graph more than once. So f is not bijective and won't have an inverse function. So this is the graph of f of x equals x squared. So y equals x squared. But f will still have an inverse relation. And that's described by this equation. So here's a graph of the equation, x equals y squared. Now notice that this graph here on the left has points negative, I guess that would be negative 2, 4, and 2, 4, and negative 1, 1, and 1, 1, and 0, 0. If I reverse the coordinates of all those points, I get 4, 2, 1, 1, 0, 0, 1, negative 1, and 4, negative 2. Notice that this graph on the right fails the vertical line test. So this is not a function. And this graph on the left is not injective. So the reason that the inverse relation is not a function is because the original function was not injective. You can see that that offending vertical line that touches the graph more than once corresponds to that offending horizontal line that touched the graph over there more than once. Now I want to talk about injective and surjective properties of inverse functions. We've discussed that when f is a bijective function, the inverse relation is qualified to be called a function, called the inverse function. And remember that the inverse function is defined this way. F inverse of y is the unique x such that f of x equals y. And we said earlier that we can say this, that this symbol, f inverse of y equals x, means the same thing as this symbol, x equals, y equals f of x. So that's an equivalent way of defining how the inverse function works. Well, it's an interesting fact about the inverse function that is often stated as a theorem in books, that if a function is bijective, then its inverse function, of course, exists. The fact is that the inverse function is also bijective. Now, its proof is really cool. It's so simple for us because we've been careful to represent our statements about function properties using precise formal logic notation. So the proof of this fact is very simple. So I've just called this fact a corollary. If a function is bijective, then its inverse function is also bijective. Let me show you the proof. Suppose that f is bijective. So we have to show that its inverse is bijective. So this is a direct proof form. Well, remember that earlier at the beginning of the video, I pointed out that the fact that a function is a function can be expressed using a quantified statement. For every x in the domain, there exists exactly one y in the range such that that y is output from that x. And the fact that a function is bijective is also expressed formally by this quantified statement. Now look at these two statements. Again, they're slightly different. The quantifier involving x is in a different place in these two expressions. One expresses the fact that f is a function. The other expresses the fact that f is bijective. Notice that both of them contain this symbol. This should say y equals f of x here. Now that symbol means the same thing as this symbol. So we can just swap out those symbols and replace them with this new symbol, because those mean the same thing. So I get new statement 1 and new statement 2 using these symbols. Now if you scrutinize these statements, this new statement 2 expresses the fact that this thing, f inverse, is a function. And this new statement 1 expresses the fact that f inverse is bijective. So there's actually nothing to this proof. We simply swapped our symbols and we found that we got the expression that we needed to show that the inverse function is bijective. Now I want to talk about what's called composition of functions. This symbol, G circle F, is spoken g composed with f. This symbol is used when f is a function from some domain S to some range t, and g is a function from some domain U to some range v, such that the image of f is contained in U. So how does that look? So here's a diagram showing that the domain of f is this set S over here, and the image of f is this set here, this red set. The range of f could be bigger. It could be this larger set, capital T. But the thing that's important is that the image of f has to be contained in this blue set that's the domain of G. So this composition is equivalent to this map. Now there's a corollary that function composition is what's called associative. That is, if you write a composition that way or this way, it doesn't matter. The result is the same. Now the way that we show that is we show that for any input, this function gives the same output as this function. And that's done here on this page. I will let you read this. Let's do an example. Let's let f be this function, the squaring function, and let's let g be this function, g of x equals x plus 1. Let's find g composed with f of x. Well, that means g of f of x. So you build this, and the result is g composed with f of x is x squared plus 1. Now let's find f composed with g of x. Well, that means f of g of x. So that means g of x squared. So you end up with this. Notice that it looks like g composed with f is not the same as f composed with g. Now, we're not positive because sometimes functions can have formulas that look different but actually describe the same function. So we should double check. We should find a value of x where the functions don't have the same value. Look, if I use x equals 1, g composed with f of 1 is the number 2. If I use x equals 1 in the other function, f composed with g of 1 is the number 4. So since the functions give different values for this particular x value, we conclude that those are not the same function. And the takeaway from this is that function composition is not commutative. It is associative, but it's not commutative. I want to talk about injective and surjective properties of compositions of functions. So suppose I have functions f and g like this, like in that drawing earlier, in that drawing. And suppose that they're both surjective. Well, then it turns out that their composition, g composed with f, is also surjective. Now, how do we prove that? Well, here we have to do a direct proof. Remember the form for a direct proof. You start with the statement 1 that says, that introduces functions that are mentioned in the preamble to the proof and that satisfy the hypothesis. So in statement 1, we introduce functions that are introduced in the preamble and that satisfy the hypothesis. And we have to end the proof by having a statement that says that those functions satisfy the conclusion. Now we do our usual thing. We unpack definitions. The fact that f is surjective, we have to unpack. That means this expression. And the fact that g is surjective, we have to unpack that definition. And look at the end of the proof. We want to say this. We want to say that g composed with f is surjective. Well, we know that in order to get here, we have to previously have proven this, because that's what it really means to say that that the composition is surjective. So once we get to this statement, we can get to here by definition of surjective. Now, let's think more about the proof structure. How do we prove this? Well, to prove that, we have to introduce a random element of set V and prove that there exists an X that satisfies this property. So these steps here are in there to prove this statement. Now, I'll let you read this more carefully, but we use the stuff that we had from these first three steps. Remember, those first three steps were inevitable. We had no choice about those. We had to start with this statement, and we had to unpack those defined terms. But now we can use all three of these things as known facts, and you'll see that they get used down in this middle part of the proof. Let's go on. Another theorem that's very similar. Suppose you have functions of that type, as illustrated in that drawing earlier, and they're both injective. Well, then their composition is injective. I'll leave it to you to figure out how that's proven. It's a similar kind of thinking. You have to set up a direct proof, as we did in the previous problem, and unpack the defined terms, if there are any, at the beginning of the frame of the proof, and at the end of the proof, if there are any defined terms, you have to precede them with statements expressing what those terms really mean. So that same approach will work for this proof of theorem B. Now, once you have proven theorem B, you've got theorem A that says if F and G are surjective, then G composed with F is surjective. And you've got theorem B that says if F and G are injective, then G composed with F is injective. Once you've got both of those theorems, then it's clear that this is just a corollary. If F and G are both bijective, that is, they're both surjective and they're both injective, then their composition is bijective. What about the converse statements? That's an interesting question. Are the converses of any of those theorems valid as theorems? That is, given functions like that, F and G, if we know that their composition is surjective, does that imply that both functions are surjective? And if we know the composition is injective, does that imply that both F and G are injective? Because again, those are statements that would be the converses of those theorems. Now remember that the converse of a conditional statement does not mean the same thing as the original statement. The fact that the original statement is known to be true does not tell us anything about whether the converse statement is true. So the converse statement of this statement may or may not even be true. So we'd like to find out, is it? Well, to answer those questions, consider this example. In this example, we have functions f and g, whose composition is defined. Now notice that if I look at the composition is this. The composition is definitely a bijection. It is, if two inputs are different, then the resulting outputs are always different. And furthermore, notice that every element of the range can be achieved as the output for some input in the domain. So the composition is definitely a bijection. On the other hand, notice that F is not surjective because there is no input that will cause N to be output from the function F. And notice that the function G is not injective. M and N both cause an output of R. So we conclude that it's possible for the composition to be surjective without F being surjective. And it's also possible for the composition to be injective without G being injective. On the other hand, notice that in the diagram above, the function G is surjective. So this function g was not injective because m and n both give an output of r. But g is surjective. And also notice that the function f is injective. So in this diagram, f was not surjective because there was no input that would cause the value n to be output. But f is injective. Different inputs always cause different outputs. So it turns out that that behavior will always happen in compositions, and that's articulated by these two theorems. So given functions f and g like that, f has domain S and range t, and g has domain t and range v. If g composed with f is surjective, then g is surjective. And if g composed with f is injective, then this should say f is injective. So both of these theorems have statements of this form, a conditional statement. If p, then q. Remember that the conditional statement is logically equivalent to the contrapositive. If not q, then not p. It turns out that for both these theorems, the proof of the contrapositive is much easier than the proof of the original conditional statement. So I'll do that proof for theorem D on the next page. So here's theorem D. Theorem D says if g composed with f is surjective, then g is surjective. The contrapositive says if g is not surjective, then g composed with f is not surjective. So notice we're going to do a direct proof of this. So we're going to start with this. Suppose that g is not surjective, and we're going to end with this. Therefore, g composed with f is not surjective. Well, so what does it mean to say that g is not surjective? We have to unpack that defined term. Well, to say that g is not surjective means that there exists an element v that's in the range of g that can never be achieved as an output of g. So for all t, g of t is not equal to v. So that means that in particular, if I want to try, instead of using the letter t there, I can put anything that I want in there, and I will end up with g of anything is never going to equal v. Well, so if the thing inside of g is an f of s for some s in set capital S, then it doesn't matter. Still, I've got this expression inside of a g, and the result is never going to equal v. So in other words, no matter what value I try for my value of little s, if I compute this expression, I don't get v as the output. That means that we found an element of the range. We found this v such that regardless of which value of the input I try, I don't get that value of the input. So that's the proof that if g is not surjective, then the composition is also not surjective. And that's the contrapositive of the thing that I really wanted to prove. If the composition is surjective, then g is surjective. And as I mentioned on the previous page, it's possible to prove theorem E by proving the contrapositive as well. I'll leave that for you to figure out. Finally, I want to talk about the relationship between function composition and inverse functions. This theorem is stated in the book, and it's proven there. if f is a function from some set x to some set y, then these two statements are equivalent. Now the book says one if and only if the other. I like to say that the statements are equivalent. That is, they're either both true or they're both false. The first statement is this: f is bijective. The second statement is this: there exists some function g such that these two equations are true. These two compositions work this way. G composed with f is this identity map, and f composed with g is this identity map. The claim is 1 if and only if 2. That's the way it would the book would say it. But I like to just say that those statements are equivalent. They're either both true or they're both false. That's what it means to say 1 if and only if 2. And furthermore, if in the case that they're both true, the inverse function of f is the function g in this case. I'll leave it to you to read the book and understand the proof of that theorem. Now I want to just simply revisit an example and see how it behaves in light of that theorem. We had this function earlier, this formula with this domain and this range, and we found that that was bijective. And it had the formula for the inverse function was that. And so the domain of the inverse function is the set that was the range of the original function, and the range of the inverse function is the set that was the domain of the original function. So what I'd like to do is compute this. Well, that expression just simply means this. And if you plug in f of x in all those spots and you simplify, you just get x. So this string of equations seems to imply this. It seems to imply that f inverse of f of x is always just x. But we have to be careful. First of all, look on the right side of the very first line. We have that expression. This is defined to be that. In that expression is an f of x. The value of f of 3 is not defined because x equals 3 is not in the domain of f. So the value of this expression is not defined. So because that expression is defined to mean the same as that expression, we see that this f inverse composed with f of 3 is undefined. So in other words, in the case where x equals 3, none of this works. So we have to say that this thing is undefined. Let's look more carefully at that string of equations up above. Also notice on this line, there's an f of x minus 1 in the denominator. So all of this stuff is suspicious, because what if f of x was equal to 1? Then we'd have division by 0. But remember that that will never happen, because the range of f is all y not equal to 1. So our only problem in this computation is that it doesn't work when x is 3. So the way that f inverse composed with f works is that f inverse composed with f of x is always equal to x when x is not equal to 3, but it's undefined when x equals 3. Now, how does that result compare with the prediction of that theorem? Well, the theorem predicts that if you have the inverse function of f being the function g, then the composition should equal the identity map. That is, the theorem says this composition should equal the identity map. Now, to see if that really does work that way, we have to first understand how that function, the identity map, on the set x works. First of all, notice that the symbol x denotes the domain of the function. So the set of x, the set of real numbers that are not equal to 3. And so this function, the identity map on that set, is defined in the following way. The identity map acting on x just gives you x in all cases that little x is in the domain, capital X. But if you try to feed in an x value that's not in the domain, then you don't get an output. So in other words, this expression, the identity map acting on x, just equals x, as long as x is not equal to 3. But that whole thing is undefined when x equals 3. So look, we see that regardless of the value of x, the resulting output of this function is the same as the output of that function. So that composition of functions behaves this way, and the identity map behaves the exact same way. So those two functions always give the same output. So that's how we can say that those two functions are the same function. Now, this theorem is stated in the book. It's not proven there, I don't think, but it's interesting, so I'll prove it here. If f and h are bijections, f is a function with s as its domain and t as its range, and h is a function with t as its domain and some set v as its range. If they're bijections, then the inverse of that composition is equal to this. So what's interesting is that if you look at this symbol, it has an h on the left and an f on the right. Look at this symbol, it has an f on the left and the h on the right. So the inverse of this composition is this surprising thing. It's this composition of inverses in the backwards order. So how do we prove this? Well, notice this is a conditional statement. It says, if some stuff is true, then this is true. So we do a direct proof. We start with saying, suppose all the stuff on the hypothesis is true, and we have to end by saying that the conclusion is true. So how do we bridge this gap from this original statement to here? Well, we start by using that fact. The fact that f and h are bijections tells us that they both have inverse functions. And furthermore, look at the domain and range of those inverse functions. S is a function from s to t. F inverse is a function from t to s. And similarly for the map H inverse. So that means we can compose those functions, F inverse and H inverse, in this order. Now what happens if we park this expression to the left of that expression? Well, by associativity, we end up being able to rewrite it, and at this point, we can replace this expression with this expression. Because remember, an inverse function composed with the original function is the same as the identity map. And then we can use this fact, the identity map composed with a function is just that function. And then we use theorem 1.3.10 again to say that the function composed with its inverse is just the identity map. So what we end up having proved is that this wacky composition is just the identity map. We can do the same kind of computation and use the composition in the other order, and we find out that that composition equals that identity map. Now go back and look at theorem 1.3.10. Theorem 1.3.10 says that if you have a function f and there is some function g that works this way, then that tells you that f is a bijection, and furthermore, that g has to be the inverse function of f. So let's go back to our proof in progress. We have this composition, h composed with f, And we've got this other thing there in that green box. If I put the green box on the left of the blue circled expression, I get this identity map. If I put the green box on the right of that same circled expression, I get that identity map. Well, that theorem says that means that the thing that's in the green box, this thing, must be the inverse function of the thing in the blue circle. So in other words, this green thing can play the role. It is the inverse function for that thing. Oh, but we've already got a symbol for the inverse function for that thing. It's denoted this way. The inverse function for that is denoted this way. So what we found is the inverse function for that blue thing, and here I've made a mistake. This should say F inverse composed with H inverse. That's the end of that proof, and that's the end of the video. Thank you.